Driven by the insatiable curiosity to explore the secrets of the universe, humanity has embarked on a journey that defies the boundaries of time, seeking answers to the questions that haunt the fabric of reality. Remarkably, the James Webb Space Telescope, with its piercing eye, has just captured a glimpse of a cosmic structure that precedes the birth of stars, the celestial anomaly that appears to be older than the universe itself. You might be wondering, how could a structure be older than our universe? Is the Big Bang Theory flawed? Join us as we explore how the James Webb Telescope just detected a 13.8 billion-year-old structure and its far-reaching implications. Imagine gazing at the immense cosmic realm where stars and galaxies perform a dazzling dance of light and gravity, revealing the secrets of the past and the future. This is what the James Webb Space Telescope, a spectacular space probe, does every day, capturing and transmitting its breathtaking observations to Earth. Recently, it has unveiled a mind-defying spectacle, a 13.8 billion-year-old celestial structure that defies the very foundations of our cosmic comprehension. Through this remarkable technological marvel, we are faced with a profound cosmic mystery, a mystery that is intricately woven into the very fabric of space itself. This shocking discovery has ignited a storm of debates and explanations within the scientific community as they try to unravel the paradox of this ancient structure. Renowned scientists and notable observatories around the world are constantly flooded with questions about this perplexing phenomenon. The most popular among these questions is, how can the James Webb Telescope detect a structure that is older than the universe itself? To answer this question, we need to first zoom in on this structure. It is not a galaxy or a nebula or a black hole. It is a star, a very old and very special star. It is located over 200 light-years away, near the constellation Libra. It is called HD 140283, but it has a more fitting name, the Methuselah star, after the biblical figure who lived for 969 years. This star is not only ancient but also fast. It zooms through space at a speed of more than 800,000 kilometers per hour, revealing its dramatic history some 12 billion years ago when the precursor of our Milky Way galaxy devoured a dwarf galaxy, which was its original home. However, what makes the Methuselah star truly fascinating is not its speed but its age. It is one of the oldest celestial objects we have ever observed, and its age defies logic. According to the initial estimates, the star was around 16 billion years old, but the most recent estimate is 14.46 billion years, with an uncertainty of 0.8 billion years. This figure poses a puzzle because the age of the universe, as determined from observations of the cosmic microwave background, is around 13.8 billion years. How can a star be older than the universe itself? It seems impossible. This paradox led to questions about the star's age, the universe's age, or the accuracy of dating methods. Could the star be a remnant of a previous universe? Could the universe be older than we think? Could our dating methods be flawed? Let's explore these possibilities further. First, we need to understand that measuring the age of celestial objects is a daunting task. Stars like our Sun maintain their brightness, temperature, and size for billions of years, making age estimation difficult. Astronomers rely on subtle changes in brightness and color over time and compare these measurements to mathematical models that predict how stars change with age. One key indicator of a star's age is its spin rate over time. Stars slow down their spinning, similar to a wheel slowing down due to friction. By comparing the spin rates of stars at different ages, astronomers have established mathematical relationships to estimate their ages, a method known as gyrochronology. Another indicator of a star's age is its magnetic activity. Magnetic activity, like flares and bursts of energy on a star's surface, decreases as a star gets older. Astronomers have developed advanced techniques, such as astroseismology, to study vibrations on a star's surface caused by waves traveling through its interior. These vibrations change with a star's age, helping to estimate its age more accurately. For instance, using this method, astronomers have estimated the Sun's age to be approximately 4.58 billion years. Returning to the Methuselah star, astronomers assign such an ancient age to it by considering the population of stars it belongs to. Stars in the universe can be categorized by the amount of heavy elements or metals they contain. Our Sun is a population I star with a significant amount of heavy elements. In contrast, the Methuselah star is a population 2 star with fewer heavy elements, particularly iron. This means that the star was born before most of the heavy elements were created in the universe, which happened in the explosions of massive stars called supernovae. There is also a hypothetical class of stars called population 3 stars, which are believed to have virtually no heavy elements at all. These stars are thought to be the first ones that formed in the primordial universe shortly after the Big Bang. They were extremely massive and hot and burned their fuel very rapidly, turning hydrogen and helium into heavier elements. When they died, they exploded as supernovae, scattering some of these elements into the surrounding space. Population 2 stars emerged from the gas clouds that were slightly contaminated by these elements, while population I stars originated from the gas clouds that were further enriched by subsequent supernovae. The existence of the Methuselah star poses a perplexing question. How can it be older than the universe itself? The answer is not simple, as it involves a lot of uncertainty and assumptions. Based on the measurements from the Hubble Space Telescope, there is a 70% probability that the Methuselah star's age ranges from 13.66 billion years to 14.46 billion years. The lower bound of this range is consistent with the estimated age of the universe, which is about 13.8 billion years. However, there is also a 30% chance that the star's age falls outside this range, with a 15% chance that it is even older. Considering all the factors, there is at least a 20% possibility that the star's actual age is younger than the universe's age. This is like rolling a standard 6-sided dice and getting a 6, which is not very likely, but this also assumes that there are no other sources of error or bias in the age estimation. Nevertheless, it is undeniable that the Methuselah star is incredibly ancient. In fact, it is the oldest star in the universe with a reasonably accurate age determination. Rather than wondering if it could be more than 2 billion years older than its environment, we can approach the problem from a different angle. Could it be that the universe is not as young as scientists initially thought? In reality, it is hard to grasp the enormity of 13.8 billion years. If we compress the entire history of the universe into a cosmic calendar, with the Big Bang as the most dazzling New Year's fireworks, Earth would not show up until late December. Recorded human history would only span the last 10 seconds of December 31st. Scientists calculated the age of the universe by observing the light from stars that were born just a few 100 million years after the Big Bang. As the universe expands, it stretches this ancient light, making it redder. This is called redshift. By measuring both the distance and redshift of these stars, scientists can infer the age of the universe. However, recent findings from scientists at the University of Ottawa suggest that the universe might be much older. They proposed that it could be around 26.7 billion years old. Renata Gupta, a physics professor at the University of Ottawa, brings up an old theory from Swiss astronomer Fritz Zwicky dating back to 1929. This theory claims that photons lose energy as they travel across enormous distances in time. This contradicts the observable redshift data, but Gupta argues that by accepting this theory along with the expanding universe, we can view redshift as a mixed phenomenon that is not only caused by expansion. Increasing the universe's age could shed light on some long-standing cosmological puzzles, as well as some new ones raised by NASA's James Webb Space Telescope. Gupta arrives at the age of 26.7 billion years by combining the tired light theory with the idea of evolving coupling constants first suggested by theoretical physicist Paul Dirac, which means that particle interactions may have varied over time. It is important to note that scientists have changed their estimates of the universe's age before. For example, in the 1920s, Edwin Hubble thought the universe was only 2 billion years old. However, our methods have become more accurate over time, and doubling the universe's age is a huge jump. It remains unclear whether astronomers will change their views on the universe's age based on Gupta's work. But no matter if humanity's recorded history is equal to just 10 or 5 seconds in the grand scale of the universe, one thing is certain. The universe is an ancient and magnificent place. Shifting our focus from the age of the universe, there are some fascinating observations about the Milky Way. Recent measurements show that stars at the edge of our galaxy are moving much slower than stars in similar locations in other galaxies. There are a few possible reasons for this phenomenon. One is that our galaxy may have a very low amount of dark matter, which is the invisible substance that affects the gravitational structure of cosmic objects. Another possibility is that our knowledge of dark matter, including how much there is in the universe, may be completely wrong. This mystery stems from data collected by the European Space Agency's Gaia satellite, which gives detailed information about the speeds and positions of nearly 2 billion stars in the Milky Way. These accurate measurements have made astronomers rethink what they know about dark matter and its relationship with the cosmos. In the vast expanse of the cosmos, dark matter remains one of the most intriguing and elusive mysteries confronting modern astrophysics. Unlike ordinary matter, which makes up stars, planets, and everything visible in the universe, dark matter is invisible and does not interact with electromagnetic radiation. Its presence is inferred from gravitational effects on visible matter and the cosmic microwave background, suggesting that it constitutes about 27% of the universe's total mass energy content. The concept of dark matter was first proposed by astronomer Fritz Zwicky in the 1930s, who observed that galaxies in the Coma cluster were moving so fast that they should fly apart if only visible matter were holding them together. Zwicky hypothesized the existence of unseen Dunkel Materie, German for dark matter, to explain this gravitational anomaly. Decades later, further evidence supporting dark matter's existence came from studies of galaxy rotation curves, gravitational lensing, and the large-scale structure of the universe. One of the most compelling pieces of evidence for dark matter comes from observations of the cosmic microwave background (CMB) radiation, which is the leftover glow from the Big Bang. Tiny fluctuations in the CMB provide insights into the universe's early conditions and the distribution of matter. By studying these fluctuations, scientists can estimate the amount of dark matter present in the universe and its distribution on cosmic scales. The prevailing theory is that dark matter consists of non-baryonic particles, meaning they are not made up of protons and neutrons like ordinary matter. Several candidate particles have been proposed, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. WIMPs, in particular, are popular because they naturally arise in many theories beyond the standard model of particle physics and could potentially explain dark matter's observed properties. Efforts to detect dark matter particles directly have been ongoing for decades. Experiments like the Cryogenic Dark Matter Search, CDMS, Super CDMS, and Xenon aim to capture interactions between dark matter particles and ordinary matter using ultra-sensitive detectors buried deep underground to shield from cosmic rays. These experiments have set stringent limits on the properties of dark matter particles but have yet to conclusively detect them. On the other hand, indirect detection methods search for the products of dark matter annihilation or decay, such as gamma rays, neutrinos, or cosmic rays. Observatories like the Fermi Gamma Ray Space Telescope and the High-Altitude Water Cherenkov (HAWC) observatory are actively searching for these signals from regions of high dark matter density, such as the centers of galaxies or galaxy clusters. Despite extensive efforts, the nature of dark matter remains elusive. Its properties, such as mass and interaction strength, continue to be subjects of intense research and debate. The search for dark matter is not just about understanding the universe's composition but also about testing fundamental physics theories beyond the standard model and shedding light on the cosmic structure formation. In the context of cosmic structure formation, dark matter plays a crucial role. According to the prevailing lambda cold dark matter, lambda CDM, model, dark matter forms the scaffolding upon which galaxies and galaxy clusters assemble over cosmic time. Initially, tiny quantum fluctuations in the early universe grew under the influence of dark matter's gravitational pull, eventually forming the vast cosmic web of galaxies we observe today. Simulations based on the lambda CDM model provide detailed predictions of how galaxies and galaxy clusters form and evolve over billions of years. These simulations match observational data remarkably well, reinforcing the notion that dark matter is a fundamental component of the cosmic web structure. Moreover, dark matter's influence extends beyond galaxies. It affects the dynamics of galaxy clusters, gravitational lensing of distant objects, and even the large-scale distribution of galaxies in the universe. By studying these effects, astronomers can infer dark matter's distribution and properties on cosmic scales, providing critical insights into its role in shaping the universe's evolution. Recent advancements in observational techniques have allowed astronomers to map dark matter's distribution with unprecedented detail. Gravitational lensing, for example, uses the bending of light by massive objects like galaxy clusters to indirectly map dark matter's gravitational field. The Hubble Space Telescope and ground-based observatories have conducted deep surveys to study these lensing effects, revealing intricate patterns of dark matter around galaxies and galaxy clusters. In addition to gravitational lensing, galaxy surveys provide another powerful tool for mapping dark matter. By measuring the motions of galaxies within clusters and their spatial distribution, astronomers can infer the gravitational influence of dark matter. Surveys like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, have mapped millions of galaxies across the universe, revealing the cosmic web's filamentary structure dominated by dark matter. Furthermore, ongoing and future observatories promise to deepen our understanding of dark matter's properties and distribution. The upcoming Vera C. Rubin Observatory, formerly LSST, will conduct a decade-long survey of the entire southern sky, capturing unprecedentedly deep and wide-field images to study dark matter and its effects on cosmic structure formation. Beyond observational astronomy, theoretical physicists continue to explore alternative theories of gravity and modified forms of dark matter. Modified Newtonian dynamics, MOND, proposes that gravity behaves differently on large scales than predicted by general relativity, potentially explaining the observed dynamics of galaxies without invoking dark matter. Similarly, theories like modified gravity, MOG, and scalar field dark matter, SFDM, propose alternative explanations for dark matter's gravitational effects. SFDM suggests that dark matter consists of ultralight scalar fields that condense into a Bose-Einstein condensate, exhibiting wave-like properties on cosmic scales. While these alternative theories remain speculative, they highlight the complexities and uncertainties surrounding dark matter's nature and role in the universe. Resolving these questions will require a combination of innovative observational techniques, theoretical advancements, and interdisciplinary collaborations across astrophysics, particle physics, and cosmology. In summary, dark matter stands as one of the most profound mysteries in modern science, challenging our understanding of the universe's composition, structure, and evolution. Its existence profoundly influences cosmic structure formation, gravitational dynamics, and the fate of galaxies over billions of years. As observational capabilities and theoretical models continue to advance, the quest to unravel dark matter's secrets remains at the forefront of astrophysical research, promising profound insights into the fundamental nature of our universe.